After stellar mass black holes, neutron stars are the densest objects in the universe. Each neutron star is the compressed core of a massive star left behind after the star explodes in a supernova. Once a star runs out of fuel, its core collapses under the force of gravity while the outer layers are ejected into space. The matter at the center of a neutron star is so tightly packed that scientists still don't know what form it takes. Neutron stars get their name because, under the immense pressure, even atoms collapse. Electrons merge with atomic nuclei, converting protons into neutrons. But the extreme heat and pressure may stabilize more exotic particles that cannot exist elsewhere or even melt the particles into a swirling soup of quarks, the building blocks of these particles. What happens inside a neutron star is described by a theoretical model called the equation of state, which explains the physical processes occurring within a neutron star. The problem is, scientists don't yet know which of the hundreds of possible state models is correct. While the behavior of individual neutron stars depends on properties such as their mass or how fast they spin, all neutron stars must conform to the same equation of state. Analyzing data from ESA's Newton and NASA's Chandra missions, scientists have discovered 3 extraordinarily young and cold neutron stars that are 10 to 100 times cooler than their similar-aged counterparts. By comparing their characteristics with the cooling rates predicted by different models, the researchers conclude that the existence of these 3 oddballs rules out most proposed state equations. The young age and cold surface temperature of these 3 neutron stars can only be explained by invoking a rapid cooling mechanism. Since enhanced cooling can only be triggered by certain state equations, this allows us to exclude a significant fraction of possible models, explains astrophysicist Nondarir, who led the research group at the Institute of Space Sciences CSIC and the Institute of Space Studies of Catalonia. Unveiling the true neutron star equation of state has significant implications for the fundamental laws of the universe. Physicists don't yet know how to reconcile the theory of general relativity, which describes the effects of gravity on large scales, with quantum mechanics, which explains what happens at the particle level. Neutron stars, with their extreme densities and gravity far beyond what we can create on Earth, provide the best testing ground for this. The extreme coldness of these 3 peculiar neutron stars makes them too faint to be seen by most X-ray observatories. The superior sensitivity of Newton and Chandra made it possible not only to detect these neutron stars, but also to gather enough light to determine their temperatures and other properties, says ESA research fellow Camille Diaz, who worked on the Newton data. However, precise measurements were just the first step toward drawing conclusions about what these oddities mean for the neutron star equation of state. To this end, Nonda's research team at CSIC combined the complementary expertise of Alessio Marino, Clara Demon, and Konstantinos Kovlokis. Alessio led the effort to determine the physical properties of the neutron stars. The team inferred the temperatures of the neutron stars from the X-rays emitted from their surfaces, while the sizes and velocities of the surrounding supernova remnants provided accurate indicators of their ages.